pretty much it. That should be worth like a page or two.
Should I be including images?
Yes, preferably. Not too many. Like, might be just one for each, or maybe like you show like how they want to make like right hand grip rules. That would be a good diagram. Model effect, you may not need to, but you can show like it has like forces created using the right hand palm rule, because you need to talk about right hand palm rule, by the way. Okay. Applications. It's not for the application. I don't think it's necessary. Like you don't have to talk about why you have that. And what else? Design of the experiment. Yeah, like diagrams essential.
For the design, can I like hammer it or?
It would be better if you can draw in the on the computer or iPad these days. I've been seeing like students actually using the iPad to draw like a diagram and then put it onto the yeah, that would be better.
Oh, yeah. So you're allowed to do like hand-drawn diagrams?
Hand-drawn diagrams is okay, acceptable, but it doesn't mean it's good. Like if you don't have any like those two technologies, yeah, if you don't have any option, because when you put like a hand-drawn like a diagram on your report, it looks really messy.
Yeah.
Because of the pictures and everything. So it'd rather be like if you're using a PC, you can use the something called like the paint, the basic tools. Yeah, I actually use that sometimes. It doesn't have to be really fancy like a 3D diagrams. As long it must be by the labeled diagram. And
so can I just do it on my iPad and put it in the document?
of course you can. Yeah, iPad is a fantastic tools that you can use these days. Okay, just checking whether I'm getting. Or it's not here yet. That's odd. Okay, YouTube. Good. Hello, Orin.
Hi, sir.
How are you?
Good. How are you?
Yeah, been busy week.
Yeah.
Okay. It's just the boys in the holiday, so they'll probably join us online today. I guess. Okay, so what we're going to do today is we're going to continue on the finish of the module 6, chapter 2. So we started about the multi-factor last week. So give you some revision on like chapter 1 and chapter 2. And next week we are having a topic test up to chapter 2. So up to the multi-fact, and once we finish the chapter test, we can move on to the inductions. What week is next week? Week is 29. In February, Steph, okay. I really wish everyone's here by 5th of February so I can do some prac. Okay. Yes, we're going to do the pracs on the 3rd of February, which is a Saturday afternoon. So that's related to motor effect again too. It's good now that you have some backgrounds about motor effect, so you know what to do. After today's class, you can start writing about your background research too. That, well, this is something that I'm going to do and design it. All right, let's talk about then the chapter 1 first. Well, we learned about charged particles in either the E or the V fields. Something that's very important. Charged particle, let's think of one by one. Charged particle means either be positively or negatively charged. It doesn't really apply for the neutral charge. So we generally talk about like the electrons a lot, which is like negatively charged. We also talk about protons, that's a positively charged. And I gave you hints that exams love to use the helium nucleus or the alpha particles. That is 2 plus, so twice charge of the protons, 2 times the charge of proton, and 4 times of the mass of the proton too. So something that coming again, probably in when we finish up the module 8, and then relate to module 8 as well too. Now, inside of the E field, we learned that E field is, I'm just simply talking about electric field. The way we can think of electric field is always using that two parallel plates. That's like one side positively charged, one side negatively charged, due to that get connected to DC battery like this. And you know that electrons will move towards the proton will move towards the negative charge because opposite attracts. We learned that the force here is applied, is known as QE, where E is known to be the voltage on the where the voltage from the voltage of the battery or the electric field strength. So E is not an A, something that you should not confuse. E is not an A because when we think about this, the same as the MA, according to Newton's second law, A must be then F on M, that is, this case, QE on M, like this too. Okay, don't just think like electric field strength is same as the acceleration, which is, but they're related, but they're completely not the same. So the type of question you can get is, yes, calculation is easy. You maybe get a question like, what if electrons going into that, making a parabolic or like projectile motions? We kind of did that question. Do you remember the inkjet questions, the printer questions too? Yeah, that's the kind of typical hardest question you can get in terms of the mathematical derive. But the type of, also another type of question is you can get a scientific skills type of question. That is giving you data and ask you to plot that and find out the relationship, then find the gradients, and no, we've done that in module 5, but same thing in the module 6. Okay, that's basically what happened to E field. Now talk about the B field then. In the B field, we learned that depends on the direction of the B, electron goes in, and we can determine the direction. Now, do you remember the unfolding negatively charged? I taught you like a usual left hand, which is not official, but it's much easier and save your time quite a lot. So what do you do? FBI or right hand palm rule, which doesn't matter. So FBI goes in, I goes there. You know that electron will move downwards straight away. Use your left hand. Okay. The left hand only for the negative charge, so don't use left hand any times. Universal rule is the right hand palm rule, that we're using that right hand to find the direction that possibly charge goes into, which is moving upward like that too. So which I show you, and your homework last week was HSC question related to these again, okay? And how did you feel about those questions? I mean, those are the past 4 years HSC questions, by the way. Were they okay?
The multiple choice is kind of hard.
Yeah, multiple choice is like, I wouldn't say that's easy always though. Yeah, sometimes multiple choices are harder than the short answers in terms of the calculations. So, okay, let me just finish the explanation. We're going to go through some of the questions from your homework and then move on to the module 2. I'm in chapter 2. Okay, in this case, F equals to QVB sine theta. This is how we found the force involved there too. Again, we can use the MA. But remember that the charged particle in the B field is making what? Kind of circular motion. So instead of the saying A, we can put the AC. That stands for what? Centripetal acceleration too. Okay, or MV squared over R2, or this is the same as MV squared over R. Something related to your module 5 contents too. So you may have some various questions, but really typical type of question is, we probably haven't talked about this, combining the E field and B field together. So I show you what I mean in here. Assume that we have two E field and B field combine that together, so that we have our E field plate, electric charge plate with a positively charged and negatively charged like that. Okay, and at the same time we have a B field that's going like this. As a B field, that's an E, go like this. Now assume that electrons are shooted and moving into this direction. Step. What would be the motion of the electron when we only have that electric field? It goes up. So it will go up like this. Okay? Alright, what would be the direction of the electrons when it goes into just the B field?
Down.
Going down, okay? So going downward like this. So what you see there is two different fields are applied on the same charge electron there, creating the opposite direction forces too. Okay, if we say, if we see that, F here applied in here is, using the module 2 again, the net force would be the force from the F FBE plus force from the FB like this. Does it make sense? Okay. Now, what is the force from the electric field? That can be calculated. We found the E field over here. But just considering the direction that the this is FB, that's FE. Consider direction. The direction of the force due to the electric field is going upwards, so we're taking that as a positive direction. However, the direction for the force due to the B field is negative because it's downwards too. So considering that FE is then QE like this, plus that the minus QVB sine theta. Just apply the substitute of the values that we learned, or the formulas there. Does it make sense? Now, if you see that the electron is undeflected, which means it goes straight, you call it undeflected. If they get undeflected, that's due to that what? Think about what I mean by undeflected. There's no change in the velocity. There is no acceleration it gained. So we can say this is equals to 0 in that case. Does it make sense? Okay. Then you get the QE is simply equals to QVV sine theta. Q cancels out, and you can get the relationship due to that too. And E equals to VV sine theta, or the V is equals to EV. So the question can be varied. It can ask you like the various the type of the questions from like finding V, finding the R, and stuff like that too. Now, the only reason I explain you this now is this is also related to your module 8, known as the Thomson's experiment. Has anyone heard about Thomson's experiment before? Okay, or plum pudding model. Has anyone heard about plum pudding models? Okay, that's known as the kind of ancient, I don't say ancient, like 100 years old, like the atomic models. You learned the atomic model from chemistry. That's a Bohr's model that we learned in year 11. Schrödinger's model that we learned as well too. We're gonna do the exact same thing in the module 8 later on. But we gotta start with the Thomson's model. That is how Thomson performed the experiment and found that out the presence of something known as electron. That's how they found out, oh, this is an electron. Do we have electrons now exist? Okay, but because of that importance of that experiment, this kind of experimental setup is popularly used in exams. One more thing, you will probably see the cathode ray a lot in your you probably have your multiple choice as well too. Whenever you deal with something the cathode ray, just think that as this is a beam of the electrons. Simply electrons. Okay? And whenever you deal with the cathode ray, just think that, oh, this is an electron. Because Thomson actually performed it with the cathode ray, and they didn't know what the cathode ray is. So he did like a various multiple experiment, and that kind of concluded that that's a beam of the electron. Okay? So in science, in physics especially, we don't really use the beam of the electron, rather we use cathode ray quite a lot, kind of mix use that too. So you had your one question about cathode ray in your multiple choice. So let's go through that question first of all. So physics. Okay, so the type of question is all related. Was probably, no, not this one. I don't remember what multiple choice. Are we done? Okay. Oh. Oh, okay. Surprised that I didn't put that question in here. Okay. Let's quickly have a look at the multiple choice question. Start off from question 15, page 11 from your homework last week, please. This is like 2000, this is actually from the sample HSC question provided in 2017, before they changed the syllabus. but this is something that's very similar. Okay, a possibly charged ion traveling at 250 milliseconds is fired between the two parallel charged plates, M and N. This is also magnetic field present in the region between the two plates. So direction of the magnetic field is into the page as is shown. The ion is traveling perpendicular to both the electric and magnetic field. So can you see that? Like this is something that's very similar to what I just explained here. But the question is, the problem is, we don't know whether M and N is which is positively negative or negatively charged. So we don't really know the direction of the electric field. So I can guess the question would be like find the direction. Yeah. So electric field between the plates has magnitude of the 200 volts per meter, and the magnetic field is adjacent so that its ion passes through undeflected. Highlight that. This is the key to solve the question. Something that I explained, that when you get that, that means simply net force is a 0. That's how we represent the net force to be 0. And undeflected, sorry. So what is the magnitude of the adjacent magnetic field and the polarity to the M terminals? So, time to use your first right-hand palm rule. So remember that this is a multiple choice, so you only have a minute to solve the question. Yes, you can think about it. If that's a short answer, you probably spend like 5 minutes, but you only have 1 minute. Means that you need to eliminate some of the A, B, C, D here, so that you can just go straight to the answer really easily. How do we do that? Use your right-hand palm rule. First of all, that we have a positively charged ions, which is just simply a positive charge particle into the B field that's going into the page. Positive, use what? Use your right hand. Okay, then F, B, and I straight away is you see that B goes there, I goes there. You see that F or like palm is facing up, so you know that this will move up without the presence of the electric field.
How do you know if it's like this or this?
Why not? F, B, I. That's thumb is in what? Ion direction. So again, only for positive for your right. Left for your electrons. Say that, Steph, electron, B field go in, electron moves to the to your right, then goes downward too. Okay, you can do the usually right hand, but as I said, this is a little complicated to think about in the exam conditions too. So this is something that you can practice a lot too. Right hand and left hand. So that's going up. So to make it undeflected, should I make this to be M to be positive or negative? It should be the positive because I wanted to put it down. I want to put it down so that you make it undeflected. Think about it here. If that's a negative, you get pushed further because opposite attracts. So this needs to be negative, positive, this is negative. So polarity to the M to relative to the N, M needs to be positive, then negative. So you can now cancel out 2 of the answers that are the negative. Then when you go to left, A and C. That's how you can start it from. Okay, then what do you do? Now you need to calculate some of the values. I just explained that. This means that QE plus QVB sine theta is equals to 0, or simply saying QE is equals to QVB sine theta in this case. Okay, you may say that QVB is a positive, is a negative, doesn't really matter for this. Okay, that's important. Q cancels out. Then we know what the E is. The B, so E is equal, the B is then equals to E on, move that to the other side, E on V straight away. The V is not the voltage, it's the velocity, it's moving, it's given. The E is given at 200, velocity is given at 250. So what is it? Then 0.8. You don't need to have, you don't even have to use the calculators because that's smaller than 1. Then answer A straight away. See, 1 minute, maybe 30 seconds, 20 seconds. If you knew, if you're familiar with these kind of questions, something that comes out in HSC quite a lot, quite frequently. Yep. Okay. Okay. Don't worry about this 16 for now. Cancel that. Can just cross that question. This is more related to the module chapter 3 inductions part, the EMF. We're going to talk about the EMF later on too. So I don't like to. Okay. 17. How'd you go with the 2021 HSC question then? Okay. Confused? Was this one of the questions? Yep. Okay. It's actually the last question of the multiple choice, question 20. So I'm assuming that this is going to be actually kind of not slightly difficult. Okay, let's see. A metallic cylinder is located in the uniform magnetic field. The work function of the metal is known as the pi. Okay, we probably learned that work function. So let's write the metal work. Guess what? Okay, this is combined with module 7. Cancel this too, because that's related to the module 7 question. So sorry, I should let you know. That also combined module 6 and 7. So we're gonna come back to this, but it simply means that the energy, this is something like when you're shooting a light onto the metals, they are ejecting some electrons, like your solar panel. Okay, that's what that means. Photon means the light shooting onto the metals, and they're shooting like ejecting the electrons out from the metals too. Okay, just think like a solar panel, exactly same contents. But that's related to module 7, so let's come back to this later, once we've completed the module 7. There's so many questions actually combined together. Okay, how did you go with the 18, 2022, 2 years ago? What an explanation. This is known as the Millikan's experiment. It's part of the module 8, but it's combined using the theory based on the module 6. Okay, so Millikan performed the experiment. To briefly tell you, I will put Millikan's experiment. The aim of his experiment was that to determine the mass of the electron. Oh, sorry, the charge of electron, I should say, the charge of electron. That we know that charge of electrons now minus 1.602 times 10 to the minus 19 C. This is his achievement. Because of the Millikan's experiment, now we know that each of the charge of the electron carries that the 1.602 times 10 to the minus 19 coulomb. Okay, and how did he do that? Like he actually performed a really good experiment and kind of precisely designed. So first of all, he used something called the atomizer, simply a spray, look like this spray. Okay, that's exactly the same. But if you ever used the spray before that, you can control that, the tip, to control the size of the water vapors you can put it in. Okay, you can make it like a mist, you can make it into like a line of that too. So atomizer has the exact same function of the spray, that it will control the size of the atoms or the oil particles. Now each of the oil particles get charged by some of the X-rays. So what they do, we shoot the X-ray onto the oil particle, so it turn it into the negatively charged. Okay, we're basically like blowing all the positively charged showing onto the X-rays. Okay, then he put it into the this is the electric field. So what happened inside that is that negatively charged, which is located now in here, and he put the positively charged plate on the top, like this. Now, because it's an oil, and even though this is a mist, you probably see the water mist is falling down when you spray the mist. I show you like when you're spraying something, it's coming down. Okay, that's because like it has a bit of like the gravity, and it's a mass due to the gravity. That means of the weight force. There will be a force due to the gravity. It's pulling this one down. But because all your charge is now negatively charged due to the shown onto the X-ray, and as we place that into the electric field that's a positively charged at the top, there will be an opposite force applied on the top here as well too. That's force of the Fe. Does it make sense? Okay. Now, remember that the reason why I use atomizer is they would know that the diameter. So from the diameter, first of all, from the diameter of the, let's say, sphere, and using that, he was able to find the mass of that. Because he knew the density, like we're going to talk about it more in mathematical details later on too, but he just simply, he was using the atomizer, like controlling that. He was able to get the mass, and then from that, the net force is 0, because what happened if the F is equals to Fg, you will start to see like the oil drops are kind of levitating. It's not falling down. Because two exact forces kind of pulling and pushing. So this means that Fe is equals to Fg in that case. So here to start to see like the figures of that too. So The question's asking you like from this kind of forces they're given here. So we have the Fg due to the gravity, Fe due to the electric field, and Ff due to the frictional force, which row table shows the forces affecting the motion of the oil droplet in the direction indicated, and the relationship between these forces. So the downward force would be just simply Fg, which is greater than the frictional force. So it's either be A and B. And in case of that, Fg and that, it must be same. So answer is B for this. Again, once we completed that module 8, we're going to come back to this. I'm sorry, like there are so many combined questions in HSA, not only designed for the module 6. But this is like something what I'm talking about in importance of the module 6, and pick the module 6 as one of the hardest topic because it's easily get combined with module 7, module 5, and even module 8 too. Which means if you don't have a good basis of module 6 now, you'll be in trouble by the time like we're preparing for the trials. Because you need to come back to the module 6, study it again, and coming back to module 7. You're gonna waste lots of time. Okay? Any other questions from the homework? Steph?
How do you structure answers? Like,
What
for example, question
20.
I don't know how to structure.
Okay. Outline the similarities and differences between the effect of the electric fields and gravitational fields on matters. In your answer, refer to the definition of these fields. Okay. Let me ask you, it's a 4 marks, and it's by the law, we need to show that the marks are located for each of the questions. Okay, and not only for the HSC trials and school exams too. So think about here, it's a 4 marks in physics. Then how many points do you need to write it down? At least how many points you need to write it down in your answer? Every 4. Okay, if you have 4 marks, means you need to write down at least 4. Or sometimes up to 3, depends, like it's 3 plus explanations. Okay, so the first way you can think about structuring your answer is think about what would be the 4 points, because the marking guideline is giving you 4 exact points too. So, and then read the question after you see the marks is a 4, okay, and think about that, what would be that 4 points are. So we're given outline these similarities. Okay, we have a similarities and the differences. This gives me a clue. If I talk about the similarities plus the details, okay, so identify the similarities and then explain. Do you think I can get 2? Because the question, I'm just following what the question is asking. This is what you need to practice again too. I'm following just simply what the question is asking you to do. I'm following that. I outline the similarities between what? The electric field and gravitational field. Does it make sense? Now from here, if you don't know like a similarity and differences, that's your problem then. That means it's a lack of study. Especially the HSC examinations. Okay. What about the differences? Yeah, same. Identify, and you gotta explain that why are they making that kind of differences too. That's 4. Easy. It doesn't mean that you are able to like construct the dot points or the tables. You're not allowed to put in the dot points or the tables now. We used to do like 20 years ago, but no, you weren't even that born in the 20 years ago too. Okay, so don't complain. Because I remember I used to do that with my HSC, preparing some school exam. I was allowed to, but we kind of retaught that in the university that you're not allowed to now. Okay, so can you tell me about what are the similarities between electric field and gravitational fields? Yeah, it would be like attraction. Very good. That's attraction of the matter. And question also say that you need to define that of these fields over here. So do you think we can, for the explanation, do you think we need to define them correctly too? Yes. How do you define the electric field? That's the field of the force created from that positive and negatively charged plate, or like 2 points, that creating some kind of electrostatic attractive force, which is a type of attraction force there. What is the gravitational force? We learned in module 5. That's the attraction force in between the two matters. Okay, and do you think you need to talk about the forces that exist in between them two? You do need to talk about in the formulas. That I'm talking about F equals to QE for the electric field was F equals to GM M over R squared, both of them. Does it make sense? Okay. Every single time you're dealing with some explanations, if you know that there's a formula exists, write it down. You have nothing to lose. It will actually help you to answer the question better. So that's it. The definition, explanation, 2 marks guaranteed. Then once you complete the first part, I would say the first half. The second half would be just talk about the differences between the two. So what are the main differences between the gravitational and electric field? Gravitational field, that doesn't require any charges. Whereas electric fields must have charges because it's electric. So that will be the huge difference between two, or like distinctive, like features of those two. Then you can explain that, like for example, positively charged can be attracted to only towards the negative, but positive charge it also carries the gravity universal. Does it give you some clue about how to structure your answer then? Okay, it is very important that you critically analyze the question and the mark, because you gotta deal with the a 9 mark or 7 marker later on too, and that your question is a really really good question, Steph, because you really need to think about how you're gonna structure a 7 marker question then. If I were you taking the HSC in exam conditions, I'd probably do this in here. Why not? This section on the top of the question will not get marked, by the way. This is I'll call the planning section. Yes, guys, I really want you to see your planning. You'd plan before you write it down something. And I don't want to see any messy work like writing down, white out. Are you allowed to use a white out in this exam? I don't think you're allowed to anymore. Yeah, so because they could do to some cheating issues too. And sometimes that cannot be distinguished by the scanners these days. Okay. And remember here, it means you wrote something down and hit this much, and you realize that, oh shoot, I forgot about writing definitions. You start writing the definition here. So your answer will be here and there, kind of messy. Now, just thinking about in the perspective of the marker, okay? If you ever marked your work, or if you ever marked someone else's, then you don't know what I'm talking about too. If you see something really messy here and there, and answer sometimes located here, and then actually I saw that before, and then you should arrow down, oh, this goes there, this goes there. You know what? If I'm marking this, I cross that all out. I'm not gonna mark this. Mark is a human being. We're not a computer, so AI though, okay? Maybe it get changed in 20 years, but then not the year that you're taking HCC this year. Means that if a marker doesn't like how you wrote your answer, you get low chance to get a band 6 then, low chance to get a full mark, but even though you got the points. And means that you need to come back to the office, the staff office, and then ask you, begging for the mark. But I wrote it there. And teachers will some teachers are willing to listen to you, some teachers are willing to correct that marks for you. But guess what, HSC, you have no chance. You can't go to the Marcus room or Marcus house and, oh, but I wrote that, it's written there. Then you see that, you can't say that. So don't make that. It's good to talk about this now because we are dealing with the HSC questions, and yes, I'm dealing with the year 12 students now. Does it make sense? Okay, so make sure you plan and structure your answer properly. Something critical and make a big difference between band 5 and band 6. Oh, sorry, band 4 and band 5. Band 5 students can structure their answers, band 4 they can't. All right, anything else? All right, any questions from you? So I realized, I talked about the planning every year for past 10 years. Out of if I have 100 students, I only say 3 is only doing the planning.
Wait, can you do this question? Yeah,
21. Oh, I got the right point. Okay, right question there. Okay. A particle having a mass of m and charge q is accelerated from the rest through the potential difference V. Assume that the only force acting on the particle is due to the electric field associated with the potential difference. show that the final velocity of the particle is given by V equals to root 2qV over m, like this. Okay. Consider about what the V is. Okay, the voltage. All right, what's the voltage? How do you find the what's voltage? What did I ask? Tell you about voltage is
Like the strength of the
strength.
particle.
Strength. Okay, strength of particle. How do we determine the strength of particle? That's interesting. Do you remember I tried to simplify that voltage and current in electricity?
Mhm.
The current is like
the amount.
the amount, the quantity, how many like charge particle we have. Voltage as in if we have quantity, what is something like quality of that?
Quality, yeah.
Quality as in like, you know, strength would be like interesting, but I'd rather say it carries a greater amount of energy. In other words, greater amount of kinetic energy represented by the velocity, how fast it's moving then. So voltage was can then explain that by, you know, amount of work done by the Q. You remember this? This is the same as the delta K on the Q.
Yeah.
Now, delta K means change in difference, and the question specifically giving you that is at rest. Then initial Ki would be 0. Does it make sense? And can I just say, oh, because of that, delta K, which is K final minus K initial, in this case, would be simply K final. How to find the kinetic energy? Half mv squared. I think I'm done from here. V is equals to half mv squared over q then. With that, qv 2 over m square root is equals to v straight away. Did we learn that? We did. Did I warn you that? I did. Did we get the HAC question 2019-29? We did.
I didn't solve it like that, but I still can.
Did you use the motion equations?
Yeah.
Yeah, I think we discussed about, yes, it has a various methods, you get the same answers, that's fine. But so remember this, there will be some cases that you can't use the motion equations. You're only allowed to use this. I mean, this is much easier because motion equation takes more variables. I think I probably told you on Thursday last week about it during the chemistry too. If you have a two method, I will simply take the shortcut or the easiest way during the exam to minimize chances of making mistakes.
I didn't know the method until those days, I think.
Okay, yeah, but this is why I'm giving you a clue that we have a two. If you have a two method, consider two method, which is a good approach. There are sometimes you must use the motion equation for this type of questions too. But in case of that voltage, did you use the F equal to QE or MA equals to the acceleration? Yeah, that thing's a little complicated than what I wrote in here. Okay, and some people are not really familiar with those motion equations yet, so I'll leave that up to you. 21 done. 22. Yep. We kind of did that last week. Okay, the question that I guys, I'm like, you will get these type of questions, and we love it. So make sure you prepare them. 23. How'd you go to 24? And 25, 24 is pretty similar. Plot the data over here. So negatively charged particle were accelerated from the rest between the pair of the parallel metal plates, and potential difference between the plates were varied, and the final velocity of the plates was measured for each variations. The data in the table show the potential differences between plates and the square of the corresponding final velocity of particles. Okay, interesting. Why do we get to square that? So before you plot, I mean, like, you can't start plotting. Plotting is not a big issue, but let us consider about why you're given that the independent variable of the potential difference and dependent variable of the v square. Why? Why? I just did that here.
Yeah.
I just did that here. See that? Different year. We got similar questions too.
Mhm.
Then v squared from that, okay, I can just leave that as v squared. Velocity squared is equals to 2q voltage on the m, like this.
Yeah.
Does it make sense? Okay. Then, okay, guys, if you're like in one that writing the question, and by just reading up to here, then it's really simple. That question A must be plotting the data and put that into the line of best fit. Does it make sense? Okay, I'm talking about the really like kind of typical type of the scientific skills question that you will get. So you always get that, by the way, always get that. So in here, if you find the relationship between, follow that, v squared to the v, which is v is the velocity, by the way, to the big V here like this, okay? Can we say these two are directly proportional?
Yeah.
With the gradient of what? 2q over n. This is the constant value, isn't it? Did we go through that in module 5? That when we talk about the Newton's law of the gravitational law, that how we make the linear relationship, and so that we can determine that we can find the line of best fit, therefore find the gradient value, therefore we can find the desired answer. So I don't know what the question B is because it's kind of cut here, but by just reading that, if I'm were you like and taking the HCC, I would like, okay, the question B must be like finding at least Q or M. Okay, also the gradient value. Let's see, question B. See? Student hypothesized that charged particle are electrons. Justify whether the student's hypothesis is correct or not. Support your answer using the data provided and the relevant calculation. So, if this is a charged particle, if the charged particle is electron, that means that this must be same as 2q of the electron and m electrons 2. If it is an electron. Does it make sense? Okay, because we know that the value of the QE minus, which is charge of the electron, and mass of the electron from your formula sheets. But what if these are not the same? All right, what if these are not the same? What if your constant, which is the gradient value, is not equals to the actual the value from the electrons?
Then like the student is wrong.
The student hypothesis is wrong. That's what you need to do. School exam question? I don't think so. There's a HSC question, by the way. I'm expecting you get at least one. Oh, sorry, more than one, because you have your school exam at least twice. HSC, so 3 times. So from 3, you at least get 2 of those scientific skills questions.
What's the difference between school exam and HSC? Is it?
I can't really tell these days, and it depends on schools too. Some school trial papers are harder than, some school exams are harder than HSC, but that's for like some selective schools, more likely. Now, I probably told you before, the reason why I'm showing you like all the HSC questions is because school exams are following the standard of the HSC examinations. That's a standard. So from that, we can decide that whether it's harder than HSC or easier than the HSC. So you always need to start from the standard, which is the HSC papers, or the questions in the HSCs, okay? Scientific skills questions, by the way, there'll be more like weight on the scientific skills, giving a data plotting and what else, like analyzing the graph, because you get the question actually something known as scientific skills exams. So you will get that this year, Maureen.
Yeah.
You will get that in next term after you finish your report too. Something very similar to what you had last year in the term 4. The projectile motions. Yeah. Okay. So make sure you prepare that. 25, 26. 26 is something that we went through that. Remember this? 26. We did that together. So kind of skip that. And the rest of the questions are something unrepeatable. So this is it about the charged particle in the E field and B field. Or do you have any questions from that paper again? 27. Sure. A charged particle Q1 is fired midway between the oppositely charged plates X and Y as shown in the figure 1. The voltage between the plate is the V volt. The particle strikes plate Y at point P. The distance S and from the edge of the plate. Ignore the effect of gravity. Plate Y is then moved to the position shown in the figure 2, while the voltage between the plates remains the same. On identical plates Q2, particle Q2 is fired into the electric field in the same velocity, entering the field at the same distance from the plate X as Q1. compare the work done on the Q1 and Q2. Okay, again, probably like I said, warned you again, every single time you deal with the work done, don't get freaked out from the work done. It simply means that change in kinetic energy, or simply finding what? Every single time you do a work done, electric work done, remember that voltage equals to work done on the Q. Okay, that means you can find that work done by Q times V, work done the Q1 and Q2. I mean, doesn't really matter because it has the same voltage applied in here. Yeah, voltage doesn't get changed from the figure 1 to figure 2, so it simply be the work done would be Q1 V, which is same as Q2 V. That's it. That's the answer for A. Compare the work done to Q1 and Q2. Should I talk about it in terms of the kinetic energy? Nope. Okay. No. There's no change in the work done. Okay. And Steph, this is what I'm talking. What I'm saying about there's a certain time that you must use that formula. You can't use the motion equations that for like question type A. B, however, is using that motion equation. Compare the horizontal distance between Q1 and Q2. So, without just doing any calculation, you know that this P is moving to that. The Q1 is moving to this direction here. You can think of like this is making like a kind of projectile motions. So that's S, and let's say that's S1 and S2. Given here like that. Okay? If you realize that this is a projectile motion questions combined with the module 6. Any idea? Any ideas about this? First, let's think about here. For Q1, we know that, let's do it one by one. Q1E is equals to the force that is applied, or MA. M1, MA. Then why am I doing this? I want to find the acceleration. Or you gotta think of the consider about the velocity here, or think about the velocity given over here there. If the work done is the same, we can interpret that as this means that the same kinetic energy gained, find the kinetic energy there we gain as well too. Does it make sense? Okay, which means this is the same as the half mv squared that's reached as well. All good? Okay, so what we have to consider here is it's flying into that and fly into the plate with this direction and moves downward here. And what you know to know, the initial like Sx, which is the range, is found by the Ux times the T. Good up to this point? Okay. Now, give you like about 30 seconds to think about like how we're gonna approach to the question, because I could try to get like give you all the preparation works now. Actually, it's different work that we need to do. Okay, sorry, A is, okay, I was wrong. Okay, let's try to do the A again too. Yes, voltage is different, but I kind of underestimated like the change in the distance there. So let's think about it here. The work done in chemistry, in physics, can be calculated by the force times the distance that you're calculating. Okay, as we learned that the F is equals to the QE times that distance that it will move. Now, think about it here. This particle Q1 for Q1 is given that D is actually separation of distance 2, and it's giving it like the information that the particle shoot in the midway of the D. So D is now is replaced to the half D. So the work done will be same as QE times half of the D, like this. Where is the half of D coming from? Because D is fired in the midway. It's moved only half of that distance. Does it make sense? Okay, that's for 1. Now, substitute that E is equals to then V on the D. Then you to get D over here, the work done is equals to Q times V on D times D on 2. Cancel out the D. Then you to get 2Q over E equals to QQ. Okay, 2Q. Okay, so you get QV on the 2 like this. Okay, so that's for the work done for the Q1. For Q2, we do the exact same thing. The work done is same as the QE times that. Now think about how much is moved, because it's a fired in here, the half D. The rest of those would be 3 on 2D from the 2D minus half D. Means that it would move that 3 on 2D about this here. Does it make sense? Okay, then instead of the half D, we can put the 3 on 2, D, substitute it. Then using the E equals to V of 2, so you get then equals to Q times V on D times 3D on 2. So cancel the D again too. That's leaving that 3 on 2, Q and V. Okay, so comparing this, number 1 and 2, the work done on the Q1 is then over to work done on the Q2. Let's divide that. Let's divide like the work done on the Q2 divided by work done Q1. So that's work done on Q2 would be equals to 3 on 4. Is that actually 3 on 4? Sorry, 2B. Am I missing something? 3 on 2, 2 equals to 2D. Oh, crap. Okay, E equals to, sorry guys, it's a busy morning. For the Q2, because it's entering to the electric field as a 2D, it's actually we have to rearrange that 2D here. So it's the 2D is making the 4 like this. That makes more sense. Now, so 3 on 4, then 3 QV on 4 divided by the QV on 2 gives you a final answer. That is a 3 on 2 by cancelling out. Which means that work done on the Q2, work done on the Q2 is 3 on 2 times greater than the work done and 1. Okay, a little complicated, I know. What question was this? 20, yeah, question 34. This is the last question and question 20 HSC. But does it give you some idea that how to find again the work done to each other? Okay, I know, mathematics, philomethy, the trends of the nowadays, HSC, physics, chemistry, both of them. Now let's do B. Compare the horizontal distance between travel by Q1 and Q2. Okay, and let's bring that again. F for the Q1. For Q1. F equals to QE. That's what we learned. Okay, that is equals to QV on the D. It's not the okay, and acceleration equals to then F on M. We kind of talked about that before too. That means that put it into here, you get the QV on dm. Equation 1 for the expression for the acceleration in the B in the E field. Okay, now for Q2. Let's write it here actually for Q2. It'll be this very similar, but you have to remember that the E field strength is quite different to the what we given in figure 1 and figure 2. That E in Q2 is V on 2D. So we're going to rearrange that. The F is equals to QE again, which is the same, but this time here it'll be Q V on 2D. You get it like what I get the 2Ds from too? I'm talking about separate like the situation here. Then acceleration is again F on M. That's the same as QV on 2MD. That's equation 2. Then what we have to use here is, yes, we know that Sx is equal to uxt that we have to find in here, but to find the range, of horizontal distance, we know that what the t is. And we generally using what? The vertical displacement to find the time taken. Do you remember that from like we are dropping something top and bottom? We kind of did that many times too. In that case, why we prefer that? Because we know the uy is 0 in all the times there, and we know what to find the velocity is. If you don't know what to find the velocity is, then we know we are able to find it. Okay? So for Q1, let's have a think about here. For Q1 again, we got the acceleration ready. This is the same as the AY, the acceleration. Okay? What would be the SY? How far it would move, up or down?
Which one?
Q1. Half d. It's moving up half d, so it would be half d like this. Okay? Now, what I'm going to do from here, I'm going to put that into the formula, the motion equation, that uy t plus half ay t squared like this. Okay? Did we talk about that uy is a 0 in this case here, so make it as 0 too. The half d is then equals to half times ay, we found from the question one, this question here is qv on dm times that t squared here like this. Yep, and then you can cancel that half, and then d is equal to d can be kind of cancelled too, so move that all that too. So t is then equals to d, move that d, okay, d square m over qv on the square root of that. Okay, that's equation 3. Then Sx, which is what? Ux times the t. Can we consider too that I would say that I just leave that in here. That S is equals to, or S1, let's say S1, that's better. So use the S. S1 is equals to uxt, so we don't do the ux here, so I'm going to leave that ux times square root d square m over qv like this, equation 4. Okay, now let's do it for the Q2. For Q2 would be that sy, this time here is not a half d, it will move further that 3 on 2. 3 on 2d here like this. This means that it's the same as uyt plus half ayt squared. That's giving you that uyt 0. So 3 on 2d is then equals to, substituting this value from the 2, that half times ay qv over 2md times t squared like that. Well, okay, looks complicated. Gives you the t value is then moving all around. You get this 6d squared m over the qv and square root of that. That's equation 5. Substitute it back into the S1, so S2 is therefore ux times the t, the ux times that square root of the 6d square m over qv like this, equation 6. So let's compare, like if the question's asking you how far, like what the difference here. So I want to do S2 divided by S1. This is giving you, this is giving you the uxt on the top. So 6d square m over qv divided by ux times d square m over qv like this. You can cancel the ux values. Okay, finding the difference, you will see like so many of those are cancelled out. Yeah, because of the square and the root, then you get the only differences of the root 6 differences. Because everything inside of the denominators and the numerator will be cancelled. Okay, you only leave that root 6. So that is the difference. Means that therefore S2 is root 6 times the S1. This is the final answer. Means that the particle in the figure 2, the Q2, will fly root 6 times of the S1. Well, by looking at this, it's like, ooh, is this like some sort of like university, like a physics? Unfortunately not. Okay, and this is what I'm talking about. It's getting physics is getting methier. That you actually need to have a really good mathematical background to do physics well. Not the physics well, like exam well. To solve the questions like this. It's hard to think about it here by step. Did I use something that new contents here? Is this like something that we covered in module 6? That's something covered in the module 5. See, this is why I'm picking the module 5 and 6 combination could be the worst scenario in your HSC like this. Because I remember that 34 in 2020, what question, 6 marks. Some people found it really interesting. Found that like, oh, wow, this is something that, you remember the Inc Z question? Yeah, they found, oh, okay, I kind of did that similar question. That question-wise, like combining the projectile motions to the module 6 contents too. Okay, if I just put the Inc Z here, this is actually exactly the same in terms of the working out in here. So I'm expecting that you get these type of questions again and repairing again. That was 2020, 21, 22, 23. We haven't had the driving questions like this for a while. So good chance for this year. But don't get afraid, try it, get a mistake and you fix it, so you improve. That's something that's very important dealing with these type of questions again, especially the HSC, okay? Yeah, okay, any other questions? The next question is pretty straightforward, 28. So we kind of did that question, so they're kind of popular. 29, I talked about the 29. So it shouldn't be a big issue for now. Okay,
Yep.
everyone good? Okay, all right then. Let's move on to the chapter 2. And I collect your homeworks and then give your marks back today. For those HSC questions, by the way, there's a good chance that I will recycle them, reuse that question in your module test and topic test too. So yeah, I want you to repeat the questions and try it again. If you're not too sure how to do it, if you're like 100% certain, then no, you save your time. So next week again, we're gonna have a test up to chapter 2. For those who are missing out the test due to like you're like in the holiday, you need to organize your time, come back, and take your test. It's your responsibility. That I will not ask you to when to come back with your test. It's from year 12. Okay, if you're serious about your studying, then be responsible. Okay, chapter 2 is about the motor effect. Okay, let's get it tight about this concept here, the motor effect. Whenever we say the motor effect, it's producing some motion. So it means this is basically a combination, like a interaction between I and the B. The I stands for the current and the B. So whenever we're dealing with the I, means that this would be current carrying, sometimes known as current carrying conductors. Otherwise, okay, if we have something like insulate, like a piece of plastic into the B field, well, we don't get the motor effect. It's same as you put the piece of the plastic bottle into the magnetic field, you don't see anything too. But what we learning here is when we put it into wire, electrical wire that carries the current in a certain direction, and put it into the magnetic field with the good angles, they will produce the force from it. Okay, and the reason behind that is because whenever we have a I, so let's write it down. This is external B. When we have an I, it produces something known as induced B field. You should know the difference between induced and external B field. So I kind of show you that in your motor diagram too. When I said the external B field, this is external B field from any of the permanent magnets simply. Okay, induced B field is when this is connected to current. This will have these couple wires will have now some current, and therefore the induced B field too. Okay, that induced B field will interact with the external B field, as we learned in law of the magnetism, the opposite side attract. Okay, sorry, the same side will opposite attract, and the same side will repel too. We use the same rules applied here, so they will repel and or like attract too. So we learned that that when we place the current carrying wire in the external field, first of all, B field, external B field going into the page. Okay, placing a current carrying wire, that current goes in here. Again, whenever you're dealing with the current positively charged, use your right hand palm rule. Okay, right hand. How do we determine the directions? Easy, F, B, and I. F, B, and I. B going into the page, I coming up, so my middle finger, palms facing that word too. Which means it makes the force they're creating to this direction. Does it make sense? Okay, so that's how we can determine, and the magnitude is simply F equals to, originated from the QVB sine theta, but this will be IL sine theta, like this. Too easy. Where the I stands for the strength of the current, L stands for the length of the wire, because think about here, if you have a longer length, it actually creates a greater amount of force too. But greater the B, yeah, creates a greater amount of force as well too. Okay? And then we also talked about the two wires carrying two conducting carrying wires. Okay, do you remember? Like, I can ask you to memorize that. Okay, the same side, attract or repel? Repel, and opposite? Really?
I mean, other way around.
It's other way around for this. The same side moving in the same direction, this case will attract. Okay, again, I can prove that. Show you using your right hand grip rule to determine the direction. So this will making it into the page, out of the page. So these two will attract to each other. In this case, it would be same side going this, so they will repel to each other. Please, yeah. I know it's okay. I told you it's gonna confuse you a lot because we have many directions involving too. But this is the kind of typical type of questions that you get, and it's good to memorize that as, oh, we have two current parallel wires, same direction of the current will repel. Okay, opposite direction will, attract and repel in that case. Okay, and we also learned about the force involved in here, that F1L is equals to mu naught I1 I2 over 4 pi r. Is something that we learned. Okay, I just quickly check with the formula sheet. I don't want to get it wrong. 4 pi r F1L. Sorry, 2 pi r. Yeah, I was getting confused about 2 and 4. 2 pi r there, or sometimes known as the K I1 I2 over r, like this. That K is like an old-fashioned, like an old syllabus. So, but you probably seen like the really old syllabus, old textbooks too. But we prefer to use that now. But simply, the mu naught is known as 2 pi times the some value. It's actually given on the formula sheet. Let's get started with that. Mu naught is given as 4 pi times 10 to the power minus 7. Okay. And K is therefore known as 2 pi times 10 to the power minus 7 too. Do not have to memorize those values at all too, okay? I mean, this is all given in the formula sheet. I won't ask you to memorize some of the formulas and values in the formula sheet, except some cases too. But that means that, yes?
K is just 2 times 10.
It would be 2, oh sorry, yeah, 2 times 10 to the power 7, my bad, been a while. Okay, in your calculation, you can just simply use the values, cancel the pi's out too, but you're not really, okay, officially, you're not allowed to use this formula now because it's out of syllabus. Just like left-hand palm rule, left-hand like a grip rule too. But who cares? Like if you can save like 10 seconds for using that, use it. If you're like kind of familiar with using the formulas, use it. All right. Now, means that we are able to find the forces interacting to each other over here, and I kind of briefly explained that how we actually found the standard unit of the ampere that I asked you to highlight and ask you to memorize too. That we set it up to for 1 meter wire when this is force is exactly 2 times 10 to the power minus 7 Newton between the two parallel wires. We define that is the exactly 1 ampere. Okay, and that uses the Newton's third law, the action and reaction force. When this is applying the action force towards to that, it will apply the exact same amount of force in different direction, opposite direction, according to Newton's third law too. We actually had to try out questions about it too, so we will have a chance to come back to the quiz question again, but we rarely get that. Okay, so that's where we're up to, technically, in terms of the theory and the content history. There's nothing really fancy. I mean, It's pretty like straightforward if I just looking at the formula and looking at this diagram too. But the HSC question ain't not that straightforward. So let's have a think about the questions that you get. I go through one of the questions today. So from that chapter 2, did I give you the new set on HSC? Yeah, you just got it on your table. And I uploaded this on your class 365. So you can download that too. It's your homework. Again, collection of the HSC questions for the past 4 years. Let's go see. Page 12. Sorry, page 13, actually. Page 13, question 16, please. Alright, two parallel conducting rods are connected by the wire as shown and carry the current I. They are separated by distance d and they repel each other with the force of F. So which graph best shows how the current I would need to be varied with distance d keep the force F constant? Okay, multiple choice question, sample HSC again too. Okay, it looked like, oh wow, why we get so many graphs here? So have a think about it here. If you're given the questions like this, you should know what the formulas are. The F on L equals to mu naught I1 I2 over 2 pi r. This is the formula that you have to use. And second of all, guys, what's the relationship between this copper wire and this top and bottom copper wires? If they're connected in the same power supply, they would have exact amount of the current. That means if you have I1 and I2, can we say I1 is equal to I2? Because they're in the same power source, basically they're connected. But the direction is opposite. If that flows in this direction from the battery, it goes that direction. So the opposite means they will repel to. It's actually given in the questions too. Does it make sense? Okay. Now we have a separation of the D between them. So what we have to do, R is then equals to D. That's a separation between that. 2 pi r is not like in the radius. It's make sure we're talking about different distance between two wires. All right. If we go up to this point in here, then the question is asking you, hey, I want to see the relation between I and the D. I and the D. So what we have to do is from 1, you can rearrange that in the subject to the I. That I1, I2 is equals to F times 2 pi r over F on L times 2 pi over mu naught like this there. Okay, now we consider that I1 is equal to I2. Can we just say, oh, this is the same as the I squared?
Yeah.
Simply the I squared. Then it is equals to F times the L times that 2 pi and mu naught times the R like this. Okay, what is F? F is constant. That's given. L is constant. L is constant. Pi is constant. Mu naught is constant too. So what is this? This is constant.
Yeah.
See, scientific skills again. That's what you need to do. Then you got to think about the relation between I square and D. So I square is directly proportional to the R, but you need to plot that, the I, to the S, that R there. So can we say I is then that constant times that square root of the R like this? Is this what? Y equals to root x forms of the graph. Then what is the shape of this? What is the shape of the y equals to root x? D. D is the answer there. Scientific skills, again, using that. So this is what I'm talking about. The concept-wise is pretty straightforward. The questions are not. So you have to think that really quickly because only you have 1 minute. So you have to process that really quickly. And I really recommend you, like, if you're not too sure, if you cannot solve that within 1 minute, guess any and move on for the multiple choice. don't waste you too much time with the multiple choice questions again. Okay, let's do one more. Okay, sorry, let's move on to the previous one, 12, 15. Give me 1 minute, actually 2 minutes, read and try that. Okay, 15. In a thought experiment, two identical parallel aluminum rods, X and Y, are carried electric currents of the equal magnitude. Rod X reset on a table, rod Y remains stationary vertically above X. As a result of the magnetic interaction, the masses of the connecting wires are negligible. So, mass of the connecting wires are negligible. It's something that we have to consider here. Okay, which statement must be correct if the rod Y is stationary? It is stationary. Okay, does anyone understand what's going on in here? Okay, we have two wires connected to the current, equal magnitude. So let's say I1 and I2. As I1 is equals to I2 again. Rod X rests on the table, X remains stationary vertically above X, and as a result of the magnetic interaction. Okay. Okay. Are we given the magnetic interaction current the equal magnitude and result of magnetic interactions? Must be correct if the rod X, Y is stationary. Oh, sorry, like, I was thinking of like a wrong question there. Okay. Let us think of like what happens to this couple Y, okay? That it has, it's just say, given a stationary, okay, meaning of the stationary, let's consider about what we mean by stationary. Okay, the meaning of stationary means that it has net force be 0. Okay, something we learned. Again, means that there are probably the forces acting on this Y, but kind of cancelling out each other, so it's making it stationary. So this is kind of weird. This looks like it's kind of floating on the top. Above the and Y is kind of floating above the wire X. Can you imagine that? Okay, means that couple Y is the connecting wire. Okay, this has the coming like force due to the gravity, kind of always pushing it down. But because we have an equal amount of force that's moving opposite direction to the gravitational force, that's probably due to the from the magnetic field or the B from the east over here. This is what the question is saying here. Okay, so if this is really strong enough, it's able to make the copper Y, the aluminum Y wire be levitating above the X. So what that means is the net force is 0. It means the amount of force Fg is equals to the amount of B goes like that in terms of the forces applied. But it's not about finding doing any calculations, more about the concepts. So think about the direction. If the force of the gravity is pushing it down, moving downwards here, and let's make the direction of the magnetic force going upwards, yep, that means that it has equal amount of force FB pushing it down as well too. Can you see, like according to the Newton's third law? Then what would be the direction of the currents if they're repelling each other? Would it be the same or the opposite step? If they're repelling, the direction of the currents, they're the opposite too. Okay, this is why I ask you to memorize that. Okay, so you see this, if this goes in this direction, current I, that's going the opposite direction there. That's what that meant in here. So after when you understand the question there, magnetic force acting on the X is X, no, it's going downward. A cannot be the answer then. The current through the X and Y are in the same direction, no, it cannot be. Okay, we can eliminate A and B. And the force the table exerts on X is equal and opposite to the total weights of the X and Y. Is that really? The force that a table exerted on the X is equal and opposite to the total weight of X and the Y. Not really. It's not the weight force. It will be like the force of the, if the Y or X is kind of pushed in the tables, it has resulting FB. There will be normal reaction force applied from that. Okay, that will be the force of the weight of the X plus the force due to the V. So the correct answer is the D. Equal to opposite to the force of the gravity acting on the Y too. Okay, tricky. Last year, just like the really fresh question from 2023 HSC question 60. Okay, tricky, but again, I'm using that what we learned about forces, what we learned about two parallel conductors, and this is how like isn't that quite creative that how examiners making the questions do, like mix and jumbles and everything, and creating the different type of questions every single time. To the force of the gravity acting, okay, and X is equal and opposite to the force of gravity and acting on Y. Yeah, so D is the right answer. Okay, any questions about this type of the questions again? Question 15. Hang on, let's check. The force in the table exerted on X, R, is equal and opposite to the total weight of the X. Yes, total X and Y. Opposite to, total equal to the force of the gravity acting on Y only. Oh, sorry, this is actually C is the answer. Correct that. I missed that. If that's on Y and X, that'll be D is the right answer, but it should be total weight on X and Y. Because what we know is for Y, the gravitational force is equal to the same magnet FB. So in that case, of the alpha Y2, so that means FB is equals to FGY, the total force on Y. X would be WX plus the gravitational Y2, which is C is the answer there. Yeah, so that's a little like trick twist in that. Again, to solve the question within the 1 minute, it's either you fully understand the contents or you're gonna see a D left. You know, and if you know like running out of time, you only have 10 seconds and you have no clue, just guess for C. Okay, and come back later if you have something like some spare time. All right, shall we have a short break, 5 minutes, and then let's do some questions at the back, and the rest is your homework. We're gonna start with a question from page 22, question 25, after break. After break. Okay, now what I want you to do now is from your, let's see the page number. Okay, I would like to try from page 22, question 25. There are 4 questions, 25, 26, 27, and up to 30. So how many? 6. Okay, try 6 questions. I'll give you about 20, 30 minutes for now, and we're gonna go through the answers together. Actually, I can give you 30 minutes. Okay, 25. Let's start from that. A copper rod is placed on a wooden frame, which is placed on a electronic balance. A length of 0.2 meters of the rod passes at the right angle to a horizontal magnetic field. So when a current of the 0.3 ampere is passed through the rod, the reading on the balance increased by 7.5 times 10 to the power minus 4 kilo. Please highlight the unit they're using, that because we need to find that something very different later on. That what is the strength of the direction of the magnetic field? Okay. First, do you guys understand what's going on in this question? Or do you understand what is going on in here? Steph, do you understand what is going on in here? This is something really similar to your practice. So, like, try to understand the background of that we have a current this is a wire, like a copper wire, it's going into this direction, placing the magnetic field about length of the 0.2 meter. So we are not really concerning about the whole length, because we're only taking account of the region that is affected by the magnetic field. Okay, and this is the motor effect questions again too, because that's indicating the interaction between the current carrying wire and the magnetic field in here. What we have to notice that is there's a balance that increased the number by 7.5 times 10 to the power minus 4 kilo. So let us think about what you mean by increase in the mass. That means that there will be greater force exerted due to the greater force exerted downward. Does it make sense? As we pressing it down, you increase the number that you're reading on the electronic balance or scales, same thing. That means that the force due to the interaction due to the B field, or due to the motor effect, must be same as the amount of the force, the weight that is gained. Now, when I'm talking about weight, I'm not dealing with the unit of the kilogram. This is a basic now. I mean, I can't explain more. This is basic because weight is simply the force due to the gravity, again, that is what? mg. Not the m. Don't just put the m value to your force value, because I never told you in that way. I've been warning you that guys be careful, like weight is different to the mass. Okay? That's from year 11, by the way. What that means is, therefore, the force exerted here is same as the mg. That force due to the B field can be calculated by BIL sine theta. Does it make sense? Okay, that means, and then we have the theta is 90 degrees because they're perpendicular to each other. So what we have now to find the B is then equals to mg divided by IL. The m is given as 7.5 times 10 to the power minus 4 times g, 9.8, divided by I that we're given is the 0.3. The length of the 0.2 meter only. We only take account of the region that affected. Then you get 0.1225 Tesla. Given the suffix of the 2, this is same as 0.12 Tesla. Now, direction. The current goes to this direction here. The force is showing in the direction of the force here. So again, use your right hand palm rule. This time, we got to figure out the direction of the B field, which is your index finger or the fingers. F, B, and I. I is showing they go into this direction. Force is indicating going downwards or going palm downwards. The magnetic field is going into the page. Okay, that's for question 25. Easy. 26. Two thin metal tubes are meter long, were supported in the vertical wooden racks as shown in the diagram. So two ends were connected together, and the other two ends were connected briefly to a car battery as shown in the diagram there. It was observed that one of the tubes jumps upwards as the connection was made. Okay, so you can imagine that one of those like moving up, like jumping, simply because we have the opposite direction current flow in the two parallel conductors, so making what? Repulsive force between them. A, explain why on one jump upwards, because we have to start here. The current First of all is flowed in the opposite direction through the roads. Okay, and resulting them to have a repulsive force. Okay, so what happened? There's a force, therefore, a force on the upper road is upwards, applied upwards. At the same time, the force on the down, the lower road is applied downward. Okay, the upper road will now be like will move or jump upwards as it does not have any support, have any upward support. As you can see from the diagram there, and but downward ones, downward road will be stationary as it is supported downwards like this. Okay, so kind of full explanation like from the what causes that, having the forces in the which directions, why. Okay, the question didn't specify which road is going upwards, so it is your task that you need to identify which will go up, which will go move like the stationary. You need to identify that the up one would move upwards due to that it doesn't have any support up there. Okay, so you see like kind of jumping, but whereas this is moving downwards, it's kind of supported by the clip or like the plate, so you wouldn't have any. Well, you can see them vibration though technically, but you wouldn't see like it's falling down. B, each tube has a mass of the 1 × 10⁻² kg, and the tube lies on the rack of the 10 centimeters apart. So this means 10 centimeters there. Okay, what minimum current flows when one tube jump? So to be able to make this tube to be jump out of the rack, you got to think about this is actually before we were connected to the current here. It was applied some gravitational force applied there. So the minimum force required to make the road to jump is exactly started from that exact mass of the great force of the road as well too. So it's somewhat very similar to the previous question too, even though different format. The working out is actually exactly the same. So but it's very similar. Let's consider that F1L equals to mu1 I1 I2 over 2 pi r. Let's bring this one again too. Okay. And then we have F equals to mg. Now force applied on the one road on the same road is same as that we're gonna use here. The F is equals to then mu naught. Just simply use the K if you like to, I1 I2 over R times the L, where K is 2 times 10 to the power minus, check it again, 7, minus 7 if I'm correct. Yes, minus 7. Okay. Now if you use that, you can just rearrange that. This is the same as the mg that are applied. Does it make sense? Okay. Now we have to find the I value. So and what you know is I1 is equals to I2 because they are coming out from the same car battery, just having the opposite direction. So let's make it to the AI. Then therefore we can think of like Ki I square is equals to mg times the r divided by k times the l like this. Does it make sense? Okay. Mass of the road is given. Now just substitute all the values you're given. 10 to the power minus 2 times 9.8 times the distance is 10 centimeters. Make sure you convert it into the meter. That's 0.1 meter. Divided by k, 2 times 10 to the power minus 7, or we can use the mu naught and 2 pi. It's the same thing. The length of that, how much is the length? Was it given in 1 meter? Yeah, it's given 1 meter long. Where do we get it from? Read that first sentence, 1 meter long there. Yep, then this is I square. Therefore, if you use I square root of that, you get the I value. This is 221.36 ampere. Okay, given the suffix of the 1, okay, interesting. This is same as 200 amps in 1 sig. So for us in having a 1 sig fix, okay. So to achieve them, to make the jumping, so the current must be greater than 200 amps in this case. This is the final answer. Easy. I mean, kind of similar working out, but using a different, like one is using the BIL, one is different formula there. 27. Sorry, C. What is the implication of the result of the power distribution network? Okay, don't worry about the question C. That's out of syllabus now. 27, please. Okay, a question that I briefly showed you, like, and I told you that, oh yeah, we have that in HSC, and this is it. This is what we had before. So a square current carrying wire is placed in a straight current carrying conductor as shown in the diagram. So, explain how the current in the wire loop affects the straight conductor. Explain. It's not about the calculation, you need to explain it. So, two things that just remember this, the current in the same direction will produce what? They make the attraction. Okay, the current in the opposite directions, I should say, they'll move in, they'll repulsion. So, you got to think of two things here. This wire, if this is not fixed, this is kind of more flexible. These line to BC, the I2, the IBC interaction would be what? Plus these two would make an attraction. Now, should we consider about I2, the IBA, or AB? That's moving from IB to A. IAB. I'm talking about this current here. Should we consider that? Why do you think we only consider like a parallel, not like perpendicular? This is something that related to the F equals to BIL sine theta as well. That according to F equals to BIL sine theta, when the theta is 90, when the theta is 90?
1.
It's a 1. So this is the one you have like when the magnetic fields are kind of perpendicular to each other. But in a case you have this, that two wires are perpendicular to each other, because of the direction of the magnetic field produced from that would not be interacting to each other. They only affects, think about this, two wires parallel. So it has the same direction of magnetic field like this. Okay, can you see that? This is a wire, the thumb, and this is magnetic field. Now, this is what happened when they're perpendicular. They were not, okay, minimally they are interacting, or they don't like effect of the magnetic field at all too. Which means that, and the current when interacting with the current AB or current CD, there will be no attraction, no interaction. As the wires are perpendicular. And you can talk about more like the magnetic fields induced from that would not be interacting to each other at all. However, for the I plus the current from the IAD, what happened? Between I and IAD, this and that, they're moving into the opposite direction, therefore they produce something, repulsive force. Repulsion. So what we are interested here is we're going to talk about the attraction and repulsion and this. But in terms of the magnitude, this is just a simple direction. I'm going to bring this one out here. F on L equals to mu naught I1 I2 over 2 pi R. Let's bring that right here again too. What would be the relationship between F and R from that formula? Inversely proportional. So this is inversely proportional like this. Which means when the R is increased, the F is decreased. Does it make sense? Okay, so let's compare it here. From the interaction, the F of the attraction, compare that to the F of the repulsion from the given wire here. That we're given the force of attraction between I to IBC would be greater than force from the repulsive force. Simply because the distance from here to there, so R1, R2, is much bigger. Okay, means that the repulsive force is more located on the far. So during the vector diagonal forces, this would be something look like this, repulsive, but greater attractive force along the top. Does it make sense? It means that we have a greater attractive force than the repulsive force as the distance RBC to the is shorter than RAD, or distance from the AD there. So a few points. If you're looking for a structure of your answer, okay, few points. That you're gonna start from what would be the direction of the current produced from the current I to the IBC and IAD. That talk about this. The current in the same direction creates the attractive force, and current in the opposite direction have a repulsive force. Second, you can talk about like why these BA and CD would not be interacting. It's simply just they're perpendicular. The lines the wires come perpendicular, which means that they're not interacting at all due to that direction of the magnetic field produced from them. Okay, that's okay. This is out of 4 marks, by the way. This is 2 marks. Just explain that the repulsive force, attractive force, and no interaction. Okay, 3. We're gonna talk about which is greater. So this is time to bring this formula out. That explaining that the force is inversely proportional to the distance between the wire to the wires, or means that greater the distance would create the lower the force. This indicates that the force of attraction, which is closest to the wire, is greater than force of repulsive force from that bottom wire AD due to that the distance over here. And the result conclusion is then, if this is not fixed, current of loop affects a straight conductor. The straight conductor would be, what do you think? They are attractive. So this will be move towards 2. Will move towards to the square. To the square conductor. This is the final answer. Okay, so kind of typical question that you have to think about. Don't just think of underestimate the effect of the third wire. Yes, there will be some effect. So we had you can find the multiple choice questions actually is kind of similar settings, but that time you use some values to find the forces affecting them too. Okay, any questions? 27. Righty, 28. Cumberland, Steph and Kevin, I even emailed you, I even sent you, I left a message, and well, I kind of talked about it today. Okay, this is your experimental setting. something that very similar. Something, oh, we're gonna hold a copper wire. You're gonna prepare 2 copper wires, put that into the a power source, power pack that's having variable powers of the current. So yes, you've got to measure how much of the current's going in and out, and that means that's your independent variables. Okay, and then therefore you're able to measure the balancing readings too. Okay, a balance was used to investigate the relationship between the current and the force. The balance was set up with that 1 copper rod fixed to it and the second rod fixed above it, as shown in the diagram. Each rod was connected to a source of current. The diagram is not to scale. The copper rods were rigid, and which was 2.6 meter long, and they were parallel. So we're not going to use 2.6, it's too long. We'll probably use that 1 meter ideally, or even like 50 centimeters for the frac. The current in the upper rod was kept constant, with the constant at 50 amps, and different currents were passed through the lower rod, and the balance reading record for each current. The reading are given in the table below as that. So can you guys see like what's the relationship between them here? You are increasing the current in the bottom whilst keeping this to be a 50 amps, okay? And you're seeing that increase of the balance reading then going down here. So from 4.85, sorry, it's actually decrease the balance reading. Okay, so from that data given, first, let's think about what's going on in here. You're seeing that these 2 wires are having directions of the currents flowing in there, which creates the force that's going towards to each other.
Yeah.
So almost like a kind of lifting that up, so that you, as you can see from the balance reading, is getting decreased. So what is this? Again, this is related to F on L equals to mu naught I1 I2 over 2 pi r, that formula. What would be the force that equals to? The force that equals to exerted? Okay, that would be equals to amount of the weight force that is created from it. Does it make sense to all? Okay, so you are asked to then plot the data into, I'm going to put the relative direction of the current in both rows, okay, justify your answer. So as the balance reading is decreased, the force must be attractive to each other, attraction force to each other, which means same direction, the current would go into the same. Okay, so justify that because you're losing mass means there were attractive force between 2 parallel wires, therefore it is subtractive. B, plot the data on the table on the graph using the scales and axis on the, as indicated, which is good, and then add the line of the best fit. So your graph should look like this. Okay, this is what you should do. What is not really correct here is you must use X, not the plot dot, when you plot in the data. Okay, and plot in the line of best fit like this. Good. So use a pencil, obviously, an easy question once you get it. C, find the mass of the copper rod on the balance. Okay, how do you find the mass of the copper rod from the balance? Any idea? Any idea? Step, when do you think we are able to find the mass of the copper rod? The exact mass. Oh, yeah, there we go. When amps is 0, then you get the exact mass of that. So mass is the copper rod is that one. Your y-intercept. So see, it would be mass of the copper rod is somewhat like 0.5489 kg approximately, or 0.5490 kg, in that range. Okay, so that value should be greater than 0.5485, which is the mass measure in the 3 amps. All right, D. Calculate the distance between the 2 copper rods then. Okay, how are we gonna find that? Using that formula over here to find the R. We need to find what the R is. So what we given? I1 is given as 50 amps. Okay, the length of the wire is given as 2.6 meter. 2.6 meter there. And you can use the K value, because that is equals to K I1 I2 over R like this. Okay, K, that is 2 times 10 to the power minus 7 newtons per amps. Okay, that means I2 and the balancing the readings is same as the, so let's think about balance reading. As we can see that the mass is getting decreased, okay, which means as we know the mass of the copper rod, okay, we can convert it into the actual Fg, the actual weight of the copper rod, okay, means that Fg minus the magnetic force that exerted, Fb, will appear as the mass lost times the G here like this. Does it give you a clue? Okay. This is the mass from the actual mass of the copper rod. Okay. This is the force from the weight, weight. Okay, force from the magnetic field, from the I2. Does it give you a clue? Okay, that means that it's giving the mass lost times the G, which is found from your gradient value. Okay, or we can maybe do it here. F1L is given as K times I1, I2 over R like that. Let's make it subject to the I1 and I2. I2, so we need to find the R value, okay? R is then equals to F on L times that. This is a little complicated than KI1, KI1, I2 times that, L over F like this. Okay. Then that's F is equals to K L over F times I1 and I2. And this is your constant value, and that's the R value like this. But yeah, current in the raw load I, and that's enhanced mass. Okay, this question is, let's not find the gradient value because it's a little complicated if you use the gradient value to that. I mean, we'll figure out that. Instead, we've got to use the line of best fit to select that point. So if I chose the one of the say 16 amp here, it will show the indicated amount of the mass you're given. Okay, so let's do this. At the 16 amp, the mass of the mass gate was given as 0.5470 kilograms. So you're gonna reuse the line of best fit. Means that compare the two, the change in mass between the two is mass of the copper minus the mass that you gained. Means that 0.5489 minus 0.5470. This will give you that 0.0019 kg is lost. Yep. So this is what? This means that this much of the force is created, kind of exerted, or attractive force is exerted too. So this case, Fg of that is mg. That's 0.0019 times that change in the mass, change in the force. I should say change in force would be then change in the mg. That's 0.019, 9.8. Which gives you, I can leave that for now. Okay, this is same as the same as F of the B that's exerted, attraction. This is what? Same as the F mu naught I1, sorry, not the mu f, mu naught I1 I2 over 2 pi r times the L. You can use the k, I mean same as the mu naught, same thing. So let's substitute the r is then equals to mu naught I1 I2 over 2 pi times that 0.0019 times 9.8 times the L on the top. Okay, we can simply use k value, which is 2 times 10 to the power minus 7 times that. I1, that is given as, the strand 1I is given at 50, times the I2 that we chose to do the 16 amp. You can use different value from the line of misfit. It will be 16 times the length of the wire. That's what? Or 2.6 meter. That divided by 2 pi cancel out. That's giving you that 0.0019 times 9.8 like this then. Okay, this will now give you the final value of the 2.23 times 10 to the power of the minus 2 meter, which is same as that 2.23 centimeters then. So therefore, the distance between the two couple of rods is 2.23 centimeters in this case. Okay, so Steph, this is a similar setting, but you're gonna investigate, probably find the k value in your questions. That from that formula here, that's if you can find the f value, pretty much you can do that from the increase the mass. Okay, and you know what r, and you know if you're considering of the variables of the I2 from that, or I1 and I2, then you should be able to get some relationship between them. So I will explain that a little more like when we actually conduct the experiment next Saturday. Okay. All right, that's how you can do the question D. 29. Again, try to give us some really similar type of questions again. Two straight copper wires are suspended so that their lower ends dip into the conducting salt solution in the beaker as shown. The length of the straight section of each wire above the conducting salt solution is 35 centimeters and they are placed 1.5 centimeters apart. The ends of the wire do not touch the bottom of the beaker. So the two wires are connected to a DC power supply. A current of the 2 ampere flows from the battery. Calculate the magnitude and the direction of the initial forces of each wire. Okay, so simply using the Ampere's law that F equals L equals to mu naught I1 I2 over 2 pi r, or simply that is K I1 I2 over r, where the K is again 2.0 times 10 to the power minus 7 newtons per amps square, given as that. Okay, let's think about what we have. Initially we're given the 35 centimeters and they are placed 1.5 centimeters apart. So L is given as 35 centimeters. Let's compare that. 0.35 meters, that's the length of the wire. The R, which is the distance between two, is 1.5 centimeter there again too. That is 0.015 meter. We're almost done then. F is then equals to, the force between them can be calculated by K times, which is 2.0 times 10 to the power minus 7, that times current that's going in as 2. The same applies, so 2 times 2 times the length of the wire, that's length of the wire, 0.35, and divided by the R, 0.015. And you should get 1.867 times 10 to the power of the minus 5. Given that in the 2 sig figs, this is the same as 1.9 times 10 to the power minus 5 newtons in 2 sig figs then. Okay, direction. Are they in the same direction or the opposite direction? If they're connected to the same power supply, they are traveling in opposite direction.
Yeah.
They're coming from the same DC. See that? That's coming down. That's coming up like this. Okay, so you can direction of the force is therefore is outwards. Okay, so again, memorize that as same direction attract, opposite direction repel in this current carrying wires. Makes your life much happy, easy once you do it. Okay, did you guys finish up to 30?
No.
Up to 30? Okay, I'll give a little more time, about 10 more minutes, 5 or 10. So try that. Again, something that very similar to this, the pracs. This time, current the wire, field direction. Yeah, this is a little different, but you may consider that. Step, you can write it down for your report. Depends. Variable would be the force from the FG. Or change in mass values. Dependent. And the controlled variable would be, I just got briefly writing down the L, the length, R, which is the distance between two. That'll be your control variables.
So independent is
The current.
why they go into
Because what I'm planning is we're going to put the two copper wires, but they're connecting the same power supply, like this connected. So you got to determine like the relation between like the forces two. Maybe like you can set it up a different experiment, but I prefer that. So going opposite direction means what? They will repel each other, so that you will actually sort of increase the number of your scales readings. Because the scale is kind of pushing it down. Okay?
Wait, if the current is missing value, how do you change it?
We have a power pack. You can change it. By increase the voltage, we are able to change the currents too. Or you can use the ammeter to measure the change in the current too. Because this is one. This is something we can do, but yeah, I have that. Aim is obviously, you see that you're going to determine the relation between the force and the current, change in current. That would be your aim. Hypothesis, that would be what? Increase in the current would increase the force exerted. So they are directly proportional to each other. So I can just rearrange that into F is equals to mu naught 2 pi mu naught times L over 2 pi R times I1 I2, or simply I square. So what do you say? You will see that I square will be directly proportional to the F with the gradient of the mu naught L over 2 pi R. So at the end, when you're assessing your accuracy of the experiment, you're going to find this value, because we know that we're going to set the L, we're going to set the R, and that means theoretically you got this the value of the gradient. Compare it to the line of best fit gradient values too, you can find the percentage error. So that's giving you the type of the assessment, like assessing the accuracy. Validity, like if you see a direct proportional relationship, as long as they're showing a good relationship, yeah, that's fine. Okay. So can you picture that now? Can you imagine like what you need to do, like what experiment setup that we're going to do as well too, and by looking at things independent of that. Okay. Kevin, I hope you watch the video. I really do. Okay. I'm recording this, by the way. Okay, so this is your practical design. I've done almost like quarter or the half of your design thing then. Because what you need to do, this is like a kind of backbone structure. So you can start to write about introduction. Say we kind of discussed that in the beginning of the class today. The introduction, as in like the background research has the motor effect. Okay, why is you talk about the Ampere's law, because that's what we're going to use here. Okay, And yeah, I mean like applications would be enough too, diagrams preferably. And then you can talk about like, you know, some relationship. So that's more you can talk it in the discussion part later on too. So that this is a relation and this is how we found the theoretical gradient value, compare that matching to the percentage error. Does it make sense? Okay?
So into the experiment.
Yeah.
So the two axes would be I squared and
Yeah, it must be. So as you can see, this is going x-axis and y-axis. The F would be what? Same as the amount of the force that mass is gained. So I must put that delta M of G. So initially you're going to weigh the mass of the copper rod as we did in here. As it gains more mass, it means that it's increasing into weight forces as well too. Does it make sense? Okay, so you got to find a change in mass. So assume like we have a kilo of the copper rod before we conduct the experiment. You're seeing that the copper rod increase in the mass to 1.1, 1.2, 1.3, and so on. That means change in mass. You can find the gradient value from that too. Ammeter. Well, theoretically it can, but it's preferably using the digital ammeter so that we know what the current is going in. That's more exact, by the way, rather than doing some Ohm's law calculations. We can find that theoretically, but it won't be exactly the same because we don't know the exact resistance of the copper wires. So rather than we're using that some formulas, it's preferably using the digital ammeter to weight up how much of the current's going in and out. Okay. Yeah, accuracy. You get to talk about like your actual data compared it to that theoretical.
Where do you put the calibration of
Calibration is always goes to the validity because that can induce the systematic error. If you ever like something using uncalibrated tools, like if you don't uncalibrated that ammeter, for example, or the power pack, that means every single time you get to some misreadings of the values, it's leading to the inaccurate and invalid result. It won't be inaccurate though. You would see invalid result then, because you didn't see the good relation between the independent variables. Okay, make sure we keep the saying control variable, which is not a big problem. Okay, mass of that is we don't really touch that too. You can talk about the control variables too. That's more going to the validity sections. Okay, but that's pretty much design of the experiment. Something that we can easily do, but you need to actually understand the motor effect or these two questions. Otherwise, this is what I'm saying. You don't know what you're writing, and I don't want to get lost while you're writing your report. That's something terrible, because you're wasting your time. Okay, all right, let's go move on to question 30. So that was the explanation for the, that's for the Cumberland practicals they're going to do. I'm not too sure, like Andy, like he's doing the same. Ryan's not doing, Ryan did actually, so Sydney boys, they do the same, okay? But yeah. Well, let me know if you have any issues or problem there, okay? Two current carrying wires are placed parallel to each other shown below. The magnetic field is measured at the point P, a perpendicular distance of the 10 centimeter from wire B and a perpendicular distance D from wire A. Okay. Readings are taken of the magnetic field strength and the direction of FP. Due to the current in the both wires, the current in YA was varied as shown in the table below. The current in the wire B was kept constant throughout the experiment. So you see the field strength of P is getting increased as you increase the current YA because there will be a greater magnetic field kind of induced from it too. So, A, calculate the magnitude of the current in the wire B, show your working. So this is something that we're using we learned in, I'm just trying to remember like Ampere's law too. So copy this down. B is equals to, it's actually given a formula sheet. Let's use that exact value that you're given. B is known to be mu naught I over 2 pi r. That's given on your formula sheet. The B stands for the induced. The B is actually from year 11. So this is the same as to the magnitude of the current in the wire B. So for the wire B, to calculate the magnitudes, we got to take the one of the current. So when the current is in the wire A is 0, that means there's only the magnetic field induced from that B. So we're taking this point over here. Does it make sense? Okay, so this is the B value. So field strength 3.4 times 10 to the power minus 6 is same as mu naught times. So times 2 times 10 to the power minus 7 times the I we have to find divided by the distance apart in between two. That's given as 10 centimeters because we measure up to here. Okay, that's where you measured the strength of the magnetic field. So 10 centimeters, 0.1 meter then. Okay, then finding that IB is therefore is giving 1.7 amps will be given as this. Okay, that's for A. Remember that we're taking the value of the 3.4 times 10 to the power minus 6 because that's when we have no magnetic from the A and they're basically coming out from just the B itself. Question B. Plot the result on the grid below. Draw a straight line of the best fit. So this is the line of best fit that you need to draw. Make sure you put all the results in it. That should be the axis, not the dots again too. Plotting and the line of best fit look like a straight line. That uses the relation between the current wire A and field strength of P, which is directly proportional to each other. Okay, got it? Yep, it's just not easy, not hard. Okay, one more thing. It's also given like a legend here, but whenever you're dealing with a really big or small value, which is 10 to the power minus something, it's good to show like the whole numbers on your axis and leaving that 10 to the power minus 6 or 10 to the power something. Okay, we kind of did that in when we did gravitational potential energy as well too. So we're dealing with the really big and small values. So that's something the tip that you can do in the HSC because you will probably not given that values or the legends in the school exams. Okay, question C. Calculate the slope of your line of best fit. So what you do, remember that in the line of best fit, finding that, you show the 2 points, any of the 2 points. I take one of the points here, so I'm taking this point and taking another point, maybe like somewhere in here. You can make a big triangle, make a big triangle here like this, okay? Make sure you put that in the right angled triangle on the graph. We kind of discussed that as part of marking criteria. Show and mark this big triangles. I don't care, see like small triangles. As long as they are right angle triangle with a similar triangle like this, you must show that so that you can carry on to show, oh, I'm finding the gradient is equals to the dB over change in the A, change in the B over change in the I, like this, IA like this. That is what? The final minus initial, so 9.7 minus 3.4. And make sure you include that value, 10 to the power minus 6. Don't miss that. So this is why you need to read the question really carefully. And 2.9 minus 0 like this. As a result, you get to 2.17 times that, 10 to the power minus 6. Now, let's guess what would be the unit of this gradient then. The easiest way to determine the unit in physics or science is you see that what you have on your fractions, and you just think about what the units for the given, the symbols. The unit for the volts, sorry, the magnetic field is Tesla. Unit for the current is amps. So the unit must be Tesla per amps. The way we can write it is T of that. Or even if you leave that as left it as this, that's fine. This is exactly the same. Unit is important that you need to put it in to get the full mark. Let's decide whether you can get 2 marks or 1 mark only. Okay? Make sure you do that. Everyone good up to this stage? Okay. Now D, find then. Use the answer of the part C to calculate the value of the distance D. So let's calculate the distance D between the two. So let's talk about like D as in like the half of the length over here. So what we can do, what we know about those two, the dB, let's bring this one out. The magnetic field is, let's rewrite that here, known as mu naught times I over 2 pi R is given as that. So this means that, thinking about the relation between the two, that field strength is given up. This means that's same as K times IA times D, the distance R given here like this, or the D. Okay, I'm just going to talk about BA, the magnetic fields induced from the current IA again in here. But what we have to know from here is the change in B or a change in IA is something that we found in here from question C. Okay, this is the same as what? The gradient 2.717 times 10 to the power minus 6 from the question C. That gradient value is same as what? The K on R then. How do we know? We move that into here. Okay, and then that goes to bottom. So that what we get, this is same as K on R. The K is the same as 2.0 times 10 to the power minus 7 times R here again too. Therefore R, the length of the distance between two would be 2 times 10 to the power minus 7 divided by 2.17 times 10 to the power minus 6, ended up 9.2 centimeters for the final answer. Okay, so this is not about the Ampere's law, the forces too, because we're not really given the force in the question. Instead, you're given the magnetic field strength. So this is a tip that you can use that again too. In fact, we learned the induced field strength calculation in year 11. If you didn't learn that, again, this is time to, this is given on your formula sheet, by the way. Okay, so this is the reason why interaction between two magnetic field creates something very similar, the F on L equals to mu naught I1 I2 over 2 pi R. Now you can see the relation to these over here. One is talking about the forces created from the two magnetic fields. Another one is just the magnitude of the magnetic field between two. So greater the magnitude of the magnetic field means that they're more likely interacting or repelling further. Okay, for now, you don't really need to know how to derive from here to there. Okay, that's also applied to Newton's third law. But just think about like the type of question that you can possibly get. Okay, so the homework for the next week, finish up the rest of the HEC questions from up to question. We did like 6 questions today, 25 to 30. So up to page 21, it shows the questions in the past 5 years of the HEC question up to the Morton effect. As I said, we gotta have a topic test about the charge on the E and B field and the Morton effect next week. Once we complete that next week, and then we're going to move on to the electromagnetic induction. And we're going to spend quite a lot of time to study about, investigate about induction, because it will confuse you. It's like something that completely opposite coming out from it. So I'm talking about the Morton effect is how we make the motors, making the movement. From the induction part, we're going to learn about how to then produce the current, which is a generator. If you learn a little bit of the generator, we spinning, then from the spinning we create kind of bicycle spinning that create electrical power. That is a generator. So from the motion, now converted into that current, which is quite tricky and interesting. Okay, that's all for today. Evidence stuff, please make sure again copy that down. Independent, dependent, control variable. I know you did. Okay. And if you have any questions about, you can now start writing your report, that introductions and background research too. So get it checked, as you go, or like you can just submit your first draft by this Saturday. So you can give me your introduction, so you can just get a check like whether you, and then I can check that whether you have a good understanding about the prac or not. And then next week, after you have a test, after we go through some of the questions about motor effect, then we're gonna do the pracs. You gotta collect the data. What you just need to do is from that, collect up after you collecting data, you just need to just start writing a report, finalize a report. Easy. So this is what I mean by you can finish the report by week 4. All right, that's it. Thank you. Full marks, thank you. See you all later this week for chemistry.